Welcome to the APMM Virtual Conference 2021. We'd like to take a minute to highlight one of our excellent conference sponsors, GoProto, a quick-turn, on-demand, custom manufacturing source. GoProto delivers turnkey plastic and metal manufacturing solutions ranging from additive manufacturing, CNC machining, molding and casting, sheet metal forming, and a wide variety of finishing options. With locations around the world, GoProto can help you create what you have in mind. Let's hear a bit more about GoProto and their capabilities.
Dan Voorhees at Muscle & Arm Farm is a great example of the application of multi-jet fusion. He came up with a design that is a reusable zip tie. We made him some samples of his zip tie parts using multi-jet fusion. He got them back and tested them and was blown away. There was no way to really prototype it effectively without going to a costly injection mold until multi-jet fusion. They work extremely well. He's able to test them well. We were able to run a bunch of parts inexpensively before making the investment in the injection mold. He was able to take his part that is meant for injection molding and go straight into prototyping, so he didn't have to create a configuration that was just for prototyping. He used the same file that he's going to use for his production injection mold. Multi-jet fusion works perfectly as a bridge with parts that are really very usable and perform very much like their injection molded part, but very quickly without a big investment in tooling cost.
At GoProto, our mission is to solve your quick-turn manufacturing problems. That's why we developed GoQuote, the simple way to get your plastic and metal parts done right and on time. To get started, head to our GoQuote page by clicking here. There are two GoQuote options depending on your needs, Fast Quoter and Instant Quoter. Select the GoQuote Fast Quoter if you need a little extra guidance or want to work step by step with a sales engineer from the beginning. Simply fill out the appropriate fields. Be sure to indicate whether ITAR regulations or export controls are required for your parts. Upload your files. Note that the max file size is 200 megabytes. Once completed, you will receive a confirmation email and a GoProto sales engineer will follow up with you within 24 hours. Your second option is the GoQuote Instant Quoter. Select the GoQuote Instant Quoter if you need an instant price and lead time quote to get your project started. The Instant Quoter can process files for all additive and traditional manufacturing projects. However, only the additive processes are instantly quoted. Traditional manufacturing like CNC tooling and sheet metal can be spec'd out and the quote will be returned within 24 hours. Register with GoQuote by entering your contact information and desired password here. Once you've created a profile, you will be able to log in with your credentials and you'll be presented with a home screen. Here in the main menu, you can view existing quotes and orders, update your account information, and start a new quote. Click New Quote to start a new project quote. Then upload your CAD files. Once your files have successfully uploaded, we can move on to the next step. To generate a quote, first choose your quantity, then choose your process, material, finishes, then the units of measurement, and then click Get Price. If you want to compare another quantity, process, material, or finish for that part, click here. If you want to add another part to the quote, click here. At this point, if everything looks correct, click Place Order to enter and save the estimate into the system. This brings us to the order confirmation page. Review and agree to the terms and conditions. Then, select the line items of the parts you would like to order by checking the box next to it. Click on Place your order and you'll receive a confirmation page with your order number. A project manager will contact you immediately to confirm details and timing. As always, if you need any further assistance, our sales engineers are ready to counsel with you on the best process for your project. On-demand custom manufacturing with GoProto.
From everyone on the board of directors and your president, Jill Kennick, we are excited for you to join us for this valuable workshop. In today's session, Wayne Forsyth of Steelcase will be introducing us to the art of sheet metal forming and provide a detailed overview of what to know when working with sheet metal bending and forming. If you have any questions, Wayne Forsyth, as well as an APMM representative, will be available in the chat, and we encourage you to discuss the techniques presented with the other attendees. The chat will be open until the end of the hour, and after the workshop has completed, we will have open Q&A for the remainder of the time. In addition, today's session will have a giveaway of 2 Micromark 8-inch sheet metal combo shear and brakes valued at over $200, generously donated from APMM vendor partner Micromark. The combo shear and brakes will be randomly awarded to 2 attendees of today's session. If you want to be considered, head into the chat and type your full name and the hashtag #MicromarkBrake as seen on screen. We will include you in the drawing and contact you for shipping details if you are one of the lucky winners. And with that, we're off.
Hello, my name is Wayne Forsyth. Fortunate enough to be employed at the Steelcase Model Shop. Today's presentation, the fundamentals of sheet metal. We're going to go over different ways to bend metal and a few different machines that we're fortunate enough to have here. I have 20 years experience in this. As I've been in this industry for quite some time, not everybody calls everything the same exact thing. So if I use a term and my cameraman doesn't understand it, he's going to go ahead and wave to me so I can stop and explain it real quick. In this presentation today, we're going to discuss safety. We're going to discuss hand brakes, air brakes, and later we'll move over into some hydraulic brakes along with a pan brake. So we're going to go ahead and start with the air brake here. Really wish I had one of these at home. There's a really cool machine. You got 2 air cylinders in the back that will produce the pressure. I can't tell you exactly how much pressure this machine produces, but it does create a very nice 90-degree bend. This here is our hand brake, another really useful tool. It works really well with thinner gauge. It would probably bend thicker gauge if you were strong enough to manipulate the handle. Also creates a very nice bend, as you can see. Just another little tool that we happen to have here. This here is our pan brake. Ideally, this isn't what it's meant for, but for purposes of the video, we're just going to use it like this. With a pan brake, you can actually get past 90 degrees a little bit, depending on what gauge you have again and how strong you are to manipulate the material. A few terms I want to touch base on a quick minute is coining, tonnage bending, and air bending, and what the difference is. When you coin something, you're dropping it hard and fast all at once. So to do that, you've got to take into effect what the spring back's going to be. Most people, when they coin, will use an 88-degree tip tooling, so that when it hits that hard, it springs back to 2 degrees to give you a nice crisp 90. If you're tonnage bending, you're bending something to a ton, and you still usually have a slowdown in there. You don't hit it near as fast. The tonnage pushes it just kind of nice and easy, if you will. When you're air bending, it's to an absolute position. A lot of presses in this day and age have what they call angle mode, where you can easily adjust the angle, -1 degrees, +1 degrees, and it makes it very easy to dial it part in. All right, so today we're going to start touching base on the first thing you do when you walk up to a press. There's 3 crucial things that really will affect your safety. 1, how much tonnage is the machine set to if your machine has the capability of limiting it? What is your slowdown at? And what tooling am I going to use to run this particular job? So first thing we're going to discuss right now is what tooling you're going to use. This is a piece of 16 gauge material. I would use a 1/4 inch opening die if I'm going to do a 90-degree bend or lesser than that. We have a bunch of variations of top tooling or punches, as they're called over here. The one I'm going to use for this demonstration is kind of a big fat one and will absorb a lot of tonnage. As a general rule, 1 inch of material per 1 ton of bending strength. Sometimes it's a little bit more than that depending on the material. That's just a guideline. For the 1/8 inch material that I have hacked up over here, we're going to be using a 3/8 bottom die and the same top. Okay, so the first thing I'm going to do when I walk up to any machine that I'm just starting on is check how much tonnage the machine's set up for. This is set for 5 tons max. So there's pretty minimal chance we could get hurt. I do want to remind you at 5 tons, it's still more than enough to take your whole hand off. So we don't want to be sticking any parts of our body in the machine. On this particular machine right now, I'm running a spacer across the fingers because they don't come close enough together to catch our blank. We're going to touch a quick second here on bend loss. You would think if you have a 2-inch by 2-inch square, you set the gauges to 1 inch, you would come out with 1 inch on each side. Unfortunately, it doesn't happen like that. This is called bend loss or K-factor. And what determines your K-factor is the amount of radius that is on your tip of your tooling. You can see that this one here is sharp. It's a 15 thousandths radius. This tip here is a 0.90 thousandths radius. The bend loss with this is going to be less than with this sharp die. The reason for that is it pushes the material. It is going to keep pushing it all the way to the bottom of this V here to create a sharp 90. Then we can measure our flange sizes and see how much our bend loss actually is. So let's do that. So another thing that'll get you hurt in a hurry on a hydraulic brake press machine is what they call the slowdown. So this machine's going to move to a speed. See it hesitate. It's slowed way down above the material. You want it to slow down above the material because otherwise when that thing's moving at a good pace, it could come up, you could crash your finger right into that die. On 1/8 inch material, I've watched a guy before ram bound his thumbs right against the ram and the material actually just sliced the ends of his thumbs right off. So slow down and watching where your material is very crucial. So I have no idea what kind of depth we need, and I'm controlling that by an absolute position with this tooling. So we're going to run this down. See the slowdown kick in. Tool just seated. I don't know if the camera shows it, but I just watched the gap disappear across my piece of material where it is making the bend. So I need to change what I have my depth actually at. So let me do that a split second here. And we'll bring it back up. So I'm hitting it a little bit hard. I can tell I'm hitting it hard by the die lines on the material also. But you can see on the inside how sharp that bend actually created. So I'm going to go ahead and lighten it up a little bit so that we can figure out what our K factor is. There is no exact formula for how much do you add for 2 degrees of this. Every die sequence of utility tooling like this changes that. So I just raised it up a little bit. We're going to see how she hits until it's slowed right down. That looks a lot better to me. Put a square on it, and I'm right there. So, if our gauges are set correctly, so I have 1 inch, 100 thousandths and 3, 1 inch, and 73 thousandths. So right now, everybody's going, I thought we were going to lose material. It appears that it has gained into here. How that works is I would have had to subtract. We have a chart right here, so I'm going to cheat just a quick minute. On 11 gauge, 179 thousandths out of the blank to get it to come out perfect. That's about what we have left over here in our blank. So we've now sheared up a piece of material where we took that 180 thousandths out of the blank so that we can come up with a 2x2 blank, or 1x1, I'm sorry. It is starting at a 2 by 1.820 size blank. So when I put this in here, we're hoping to get 1 inch left on each side. So let's start the machine up. I have a pedal down here, a foot pedal, and that's how I'm controlling the ram. It's programmed to stop at a certain distance for its slowdown. And that's crucial so that your materials not come flying up at a very fast pace. So I'm now going to put that in there. One inch 11 thousandths. 1 inch 15 thousandths. So we're still just a little off, but that's fine. So that's our K factor for 11 gauge with the tooling that we're using. What if we changed gauge of material? Well, let's do that a quick second. So we hold the tooling in with just a set screw. There's not a lot of pressure on the tooling, as most of the pressure is going to come from 3-point friction bending. What I mean by that, so we have 3 points of contact bending that we're using right now in utility tooling. We'll have 1 point here, 1 point here, 1 point in the punch. So as this starts to put force on it, it's going to drag that material in, which is where you get your die lines from. And you can see, especially on this piece, where it started and moved in that little bit. So as I change this tooling over, we're going to go over this kind of slow and try to make it so everybody understands what's happening here. The tang on our tooling here at Steelcase, the part that is in the bottom bolster plate, is not always in the center of the tool here. It's just the way it was manufactured over the course of time. So the first thing we're going to do is loosen the bolster plate up. Want to make sure that it's moving nice and free. I'm then going to just seat my punch into my die. So you can hear the machine start to whine. It's got some tonnage on it. That has to pretty much be center. Just snug that up. I'm going to come back over here to my depth control. I'm going to transfer that from the ram and then add enough to guarantee we don't ton out and slice our material in half. Now we will attempt to figure out where the back gauge is and what adjustment needs to be made to that. So I am a little bit off. I don't know if you can see that pretty good. So I'm going to add a little bit more depth. You need to come down just a little bit. Again, there is no real method of how much numbers control the depth per piece of tooling. I took 3/1000ths out of it. Let's see what that does. Pretty lucky guess. And our back gauge needs to move just a little bit to keep that 1 inch. Now we'll go in and adjust that just a quick second. So now that we have a good 90, our back gauge is set at 1 inch. Now I just want to, I'm going to take some of that slowdown out so that everybody gets to see how fast this thing can move. And I just want you to imagine if your thumb was close, how fast you couldn't get it out of there before it was gone. With the tooling I'm using, taking the slowdown out and running a higher forming speed like we're about to, your repeatability goes down. The consistency of the material and the bend are going to change because it's hard for the machine to calculate that fast on the fly. Alright, my cameraman was just nice enough to point out, what if you don't know all the components of a brake press? So we're just going to back up a quick second to figure out what a few things are. This is my gauging system. This is called a back gauge. It's the same on most brake press machines. This one's a little unique in that I can make the gauges work independently or together. They will still only come within 3 inches of each other. The back gauge controls the size of the flange or the amount of bend that you're putting into something. This is called your ram. You've got 2 hydraulic cylinders up here that create, on this press it maxes out at 135 tons. So I can create up to 135 tons of pressure on the ram to the bolster plate. The bolster plate is usually what's going to hold your bottom tooling. So what I've got going right now is I just wrote a little program to demonstrate how these towers are independent and how the back gauges can be utilized in different ways. If you had an angle, let's say you had a 30-degree angle that you wanted to bend something up at, you could set your back gauges at different increments to achieve that. Not all back gauges move like this. This here is more of your traditional back gauge, one fixed back gauge instead of 2 independent towers like your last machine had. This one has 2 movements in the X and then the Y. I know it's super exciting. So you've heard me say 3-point friction bending a couple times. I just want to go over what exactly that is. You're going to have 3 points of contact. 1, 2, 3 being your punch. So as that material starts to form under the tonnage, you get the 3 points of friction. That's where your die marks are going to come from, as you can see in this part. Great thing about the Rolla V is it does eliminate a lot of those. This 3 points of contact also creates a little bit more tonnage in the parts. So I just wanted to show this part a quick second. What they wanted here was a certain diameter put into the part. They wanted to maintain the flat in between the two. So I calculated out the distance of what it should be to get the radius and how many hits. This particular part took 10 hits at 3.8 degrees to create the 38 degree not only bend, but the radius that they wanted. So I just wanted to show that you can bump bend in that style. Also, you don't always need the exact diameter radius to create one. All right, now we're going to talk about some tooling. So I hope everybody's ready for this discussion. Your top punch dictates a lot of how the part is going to come out. Well, what do you mean by that? Well, here I have a part that's kind of bent into a U-channel. With my thin punch, I could get in there, and I don't know if it would actually bend that to 90 degrees or not. Chances are it's going to start bending this flange back. So in that case, if I ran into that, I would use something called a gooseneck, which allows you to get in there and bend that and have plenty of clearance left. There are different types of goosenecks. This is for a thicker gauge of material. This is for a much taller flange, if you will. So I currently don't have a sample, but we'll make one here real shortly. But if you had to put like a hem and fold on something where the material comes 180 back to itself and then gets smashed flat, you would end up using what they call an acute die and bottom. So your punch is much sharper, tapered off, and your bottom die has a V opening that comes to a point to push the material into to collapse it to a point. So as promised, we're going to talk about some 3D printed tooling next. So this part here, as you can see, has a unique feature to it that would be really hard to get in there without having 3D printed tooling. 3D printed tooling does not absorb the tonnage that steel tooling will, but for 5-10 piece runs, it'll get you out of a bind pretty quickly, and it seems like everybody has 3D printers in this day and age. So that would have been my bottom die, and I would have pushed that in with this top piece like that. In our discoveries, 3D printed tooling works great on 16 gauge, 060, and under. Once you get into the 14 gauge, you can't get the detail such as that small little curve in this part across here where that is. It just doesn't seem to have the detail at 14 gauge. So this is a small clip that I used, made out of 3D printed tooling. Can't discuss what it goes to due to top secret rights so far. But as you can see, it has a nice arc all the way through the piece. What they wanted was something to fit in here after it had been heat treated and maintain a distance so that the screws would pull it together. And we did achieve that. How I did it was with this piece of tooling right here. As you can see, there's a small arc at the top. These two plungers push the part down, and then the tonnage from the machine, which on this part I did go up to 2 tons in my push. Then the tonnage finishes your form kind of like that. Some of these parts that I'm about to show were also made with 3D printed tooling. As you can see, this part here has a nice little emboss in it to help strengthen it up, as this was their biggest complaint, is it was weak in this region. This one here was one of the first versions, and this is what that part looked like when it was all bent up. We gave them a nice lead-in edge. This had to fit on something 3/4 inch diameter, and they wanted it taut enough that it would hold in whatever position it was oriented to. Those embosses that we just talked about go all the way back into where it starts to curl, which really helps strengthen these weak tabs up. So far, all the tooling we've talked about has been what we call utility tooling, which means it's different size bottoms and top dies. A lot of what we use for a bottom die is really just an offset die. We just happen to use the V, the open empty V end of it. So here at Steelcase, we have a bunch of 8-foot tooling. I start at a 16th offset, and this goes up to 3/8. I have another rack over there. I'm not sure if we can see that or if we need a different shot. That goes up to 5/8 of an inch. And then we start in what I call the rare ones, one-off mades. We do a lot of radius stuff, so I'm always making different radius punches. Use a lot of different bottoms for radius. And then we have what I call our 4-foot rack over here, and that's a lot of designated tooling for one-off stuff also. So we also have tooling that's smaller than 8 and 4 foot. We have drawers and drawers full of utility tooling that we still use quite a bit for a lot of different parts, even with the new tooling called precision tooling. We're going to talk about that in just a second, so hold your questions on that. We are fortunate enough, like I said, to have just drawers and drawers of different assortments of sizes and pieces. So a minute ago I had mentioned precision tooling. I want to talk about that just a quick second. Precision tooling is pre-measured tooling that is stored in a work library on this machine. And why is that important? Well, if I'm running a job every week, let's say I'm doing the same part of 16 gauge in a manufacturing facility, I can throw the tooling in and the program's going to be within 2 degrees of being perfect almost every time. So it eliminates a lot of setup time, and it really gives you a much easier to work with bend for the operator. So in precision tooling, we talked earlier on utility tooling, how the tang that goes in the bolster plate or into the ram is not always on center here. With precision tooling, you can change from a gooseneck punch to a sash punch in a matter of seconds and not lose a degree in your bend or have to recalculate your dimension flange, and you also do not have to readjust your bolster plate. This is also a form of utility tooling. They now manufacture this in a precision tooling combo also. Ours is called Roll-A-V. Wilson has a name for theirs, and I'm sure by now every tooling manufacturer is making a Roll-A-V. We talked about the 3-point contact friction bending, and how this die works is these are spring-loaded paddles that move with the part. So one, you are eliminating a lot of finish work on die lines. It also reduces your tonnage tremendously. So if you have, like the gooseneck that we were talking about earlier, let's say I'm putting too many tons on that gooseneck and taking the risk of bending it or hurting the die, I could try to switch to a Roll-A-V to eliminate some of the tonnage. All right, so now I just want to show how that Roll-A-V So you can see right here as these paddles are coming up, the springs are trying to suck it back down. And there is no die mark from it. You can see where the material is still stretched, and you're always going to see some of that. But if you had to metal finish this out, we just eliminated a lot of time of sanding in it. Very minimal die lines. It did pull these holes a little bit. That's because they're so close to the bend line. This would be way more exaggerated without using the Rolla V tooling. So here at Steelcase, we're fortunate enough to have 4 different versions of the Rolla V. Why do you need 4 versions? Depends on what material you're working with. The version 1 works great up to 18 gauge. Version 2 works great from 16 gauge to 11 gauge. The Rolla V3 works great from 16 gauge all the way up to 1/4 inch. I've bent on it. I use a lot of radius diameter tooling on it. It works really good up to 5/8 diameter with 1/8 inch steel. You start getting over that, and what'll happen is you start spreading the paddles, which hurts the die. So this is our adjustable Rolla V4. Great piece of tooling. I can't say enough about this, how much time it has saved us on big radius jobs, like a 5-inch diameter radius coming into 1/4 inch aluminum even. These things here just work great. We talked about the paddle movement earlier. It's easier to show on this one. As you can see, that paddle's just gonna roll with your material. So instead of having 3 points of friction, you're down to just the friction of the punch in the material. This adjusts all the way to closed. Any of the Rolla V product that you use, your material must span at least halfway on the paddle. If you don't do that, the paddle will actually just kind of slide out, allowing your material to not get bent. Again, I'm very disappointed we didn't get the opportunity to do this in person, as my workshop was going to be a hands-on experience. This here is the Micro Mark 8-inch mini shear bench brake, and I'm going to put a few bends on a few things. Just wanted to show you again, this was the project we were going to make in the class, and I want to go over how I was going to do some of that in a minute. The first thing I did is I made some 3D printed tooling where I incorporated a small edge here to act as my back gauge. So the first thing I'm going to do is put an acute bend on this with my 3D printed tooling. I've got a nice hollow V out here. If you're asking what's an acute angle, it's not a good looking thing like I am. Not everybody's fortunate enough to look like Uncle Fester. It is an angle that is past 90 degrees. All right, so I'm going to go ahead and make our very first acute bend, again with the 3D printed tooling. So earlier you heard me use a term called ram bind. I just wanted to take a second and explain what that is exactly, because we are there. Ram bind is when your part has exceeded its travel limit before something's going to start deforming your long flange or the flange that's in the machine. And as you can see here, we have reached that point. So anytime we put flattening dies in here, we call them the magic eraser. If you put a bend in the wrong spot, a lot of times you can wipe it out with a flattening die and make a second attempt. If you are too close to the original bend, a lot of times you'll run into where the material will just break. I'm going to put a shim in here, which is going to keep an open gap in this so that we could make our lid. So let's make this happen. When I'm bringing this down, I am not trying to really force it. I just want to bring it to clamp this material and create a nice edge so that I don't slice my hand open. I'm going to go right to about there. My material goes in and out nice, so I know this box will make a nice lid. This is the flattening die I just used. The machine itself has two different heights in the ram, so that's why my block looks the way it does, to keep it from not teetering as we fold that flange over to a hem and fold. So I tucked that little shim in here, and the reason I'm doing that is as this press makes the bend, it will close my hem because of the way the material is going to lie on it, which you'll see in just a second. So the next tool we're going to use is a 90-degree bottom. I have actually incorporated the back gauge into my 3D tooling. As in the workshop, I thought it would save a lot of setup time of moving the back gauge around. So I'm going to go ahead and do the die change and install this a quick second, and then we'll make a bend. Now we're going to go ahead and make this bend. We want this to come out as close to 90 as you can. Excuse me. You can see right here, hopefully, that shim not being in there, right here is where that hem would get closed up. So that shim's going to become really important here. We now have the start of our box lid. We've got one side done. I'll repeat this process 4 times real quick. I now have my lid complete. Got 4 hemmed over edges. Nice shallow little pan. Now we're going to move on to making the bottom. So again, I've incorporated the back gauge into my 3D printed tooling to create the bottom box here. So let's go ahead and form that up next. I just want to let everybody know I had a lot of time into figuring this box out. So as easy as it looks now, there was hours of pre-bending and failure into this before we got a winner. Ooh, we didn't get 90 degrees there. So earlier we had discussed fit tooling, and this is a perfect place where it comes into play. As I work around this part, my tooling's just small enough to fit inside of my flanges. Got a nice good corner happening. Now I got to move my bottom out of the way to get my part off, because we don't have very much stroke here. But here is our box bottom. So again, I want to thank Micromark Industries for donating 2 of these that we'll be giving away at the end of this presentation, which we are fastly approaching. I want to thank everybody for tuning in, and especially thank my cameraman, Jeff Long, who has put a few hours into making this with me also. And I want to thank the poor guy who's doing all the editing. Thank you, APMM.
And now on to the Q&A. If you haven't already, head over to the chat, either to your right if you're viewing on a desktop, or below if you're on a smartphone, and join the discussion with the presenter and your fellow model makers. When you are ready, or after the session ends, you can head to the APMM Zoom meetup for further discussion or general information from an APMM representative. This Zoom meetup will be open all day from 9 a.m. to 9 p.m. Eastern Standard Time. For future sessions, head back to the conference schedule page for dates, times, and the appropriate link for each session. And as you discuss, We want to thank the companies and individuals that have supported the APMM and our conference efforts with their donations after we had to postpone our in-person conference last year. Your support means a lot to this organization, and it helped make this conference a reality. Find the names of our amazingly generous conference donors on the screen now. As a reminder, if you want a chance to win the Micromark Sheet Metal Combo Shear and Brake, head into the chat and type your full name and the hashtag #MicromarkBrake as seen on screen, and we will include you in the drawing and contact you for shipping details if you are one of the lucky winners. Thanks for coming to this session. We hope you enjoyed it.